this is a circle. It's 2D. It has one face, and the diameter is halfway across, or all the way across, and which would be about 6 inches. The radius is half of the diameter, which would be around 3 inches, and the circumference is like a round circle, which would be 3 times of the diameter, which would be 18 inches. And it's infinite. You can cut it into infinite parts.
All right, I like it. Does anyone have anything to add about the circle? Michael did a pretty good job analyzing it and dissecting it.
It has one face.
Yeah, 2-dimensional, one face. All right, if you would, well, I put a point on it. Look at the center point, the midpoint. Now, believe it or not, that actually has there's a name for that called a centroid. You won't see that until high school geometry, but the centroid is kind of fun. But I want you to fold point A down to the centroid, fold point B to the centroid, fold point C to the centroid, and you'll make a new geometric figure. And you might have to play around with the folds a little bit. All right, beautiful.
The triangle has 3 vertexes, 3 sides. It has
Well, you didn't mess up, just mess on. What else do you notice?
All
right, think about these vertices, these angles. What kind of angles are they?
Acute.
Yes. I know we haven't used the protractor yet, but if you add all 3 of these angles together, they're going to come up with 180 degrees. Because all these angles are the same, what must each angle be? How many degrees must each of those angles be?
90 degrees.
Gia, you're shouting out, but it's not going to be 90. 60. Yeah, it's going to be 60. You see, 90 is a right angle. These are acute, so they got to be less than 90. 60 plus 60 plus 60 equals 180. All right, if you would, grab the top vertex of your triangle and just fold it down so it's in line with the base of your triangle. Yeah, Michael's got a good model going on right there if you look over his model. We made a new geometric figure. Now I guess Anum did say something about the circle this way. So let's jump over here and see if Micah can do a little analysis of the trapezoid.
This is a trapezoid, and it's a 2D shape, and it has one face. It's not a parallelogram, but it's a quadrilateral.
Why is it not a parallelogram?
Because it only has one pair of parallel sides.
Correct.
It has 4 sides and 4 vertex.
I agree. Flip it upside down. Now, what can you divide this trapezoid into?
3 triangles.
What kind of triangles are they?
Obtuse.
Well, obtuse is bigger than 90.
No,
Look at the
acute.
Yes,
Acute.
those are acute. And it looks like all the sides are the same length, so we call that an equilateral triangle. If you would, everyone flip it over so you're looking at the 3 triangles. All right, now 2 of the triangles are upright, 1 of the triangles is facing down. Are they still congruent?
Yes.
How would I move? Would I translate, rotate, or reflect these triangles to put them facing upward or facing downward?
Rotate.
Yeah, I would just turn them. I would just rotate them. Who remembers that from last year? Oh, good. Great. You guys had excellent teachers last year. If you would, grab the, it doesn't matter which one, but on the right-hand side, grab that acute triangle and fold it over to the middle. So you're going to make a new geometric shape. Something I might have called a kite, or might have called a diamond when I was a kid. And that makes a lot of sense in English, but I'm looking for someone to talk math to us.
This in math is called a rhombus. It has 4 vertexes. It's 2D. It has 1 face. And it is a parallelogram. Two of its sides are acute, and the other 2 are obtuse.
You mean the angles, yeah. No, you're right. I get what you mean. It's just hard to... Look, math has very specific vocabulary, and it's hard to talk it out with correct math. It's easy to do it in English, and it's easy to do, well, you know what I meant. It's very hard to be precise. All All right, I like it. If you would, then, let's see. What I want to do now is, if I'm looking at this, I want you to take the other part of your rhombus and fold it over the center so that you're making a small equilateral triangle. All right, looks good, looks good. Who can kind of analyze this and talk to us about this little triangle? What do you notice?
Well, it's very similar to the big triangle we made earlier, and believe it or not, that's actually what it is called, similar.
Yeah. In English, we would say it's very similar, but in math, similar means same shape, different size. It's exactly the same shape. It's just smaller. Okay, so now lay your triangle down, and we're going to be able to actually stand these triangle sides up in such a way that we make a three-dimensional figure. Go ahead and give that a go. Oh, very cool. All right, so we move from 2D to 3D. Who wants to begin this one?
This is a pyramid, and it has 4 sides on each side and the bottom. It has 4 points at
They are points where line segments come together. What do we call those points?
vertices.
Yeah, they're vertices, corners, angles.
It has. Is that all?
Okay. All the faces are the same size, so it's congruent
Yes,
faces.
congruent.
And of course, they're all equilateral acute triangles. All right, lay it down. And if you have it laying all out like Micah has, now you're going to take your vertex, if you will, and just kind of fold it to the middle. You're going to try to turn this into a hexagon now. Yeah, so watch Micah. There you go. Perfect. If you fold your 3 vertices to the center of your figure, you'll make a 6-sided shape called a hexagon. And I'll probably give you too much information. All right, and I wonder if someone will get us started dissecting this hexagon and telling us what you notice.
Well, it's obviously a parallelogram. These are parallel, these are parallel, these are parallel, and every single one of the angles is obtuse. Did I get that right?
You did?
And,
Excellent job. Who has something else to add to that, perhaps? Gee, that is excellent.
It's 2D and it has 1 face.
It does. All right, I'm going to stop the video now so you guys can wave to your co-teachers here. And let's see.